So there is a view somewhere on the top. Probably not there. Yeah. Good. Can I use the clicker? Just to verify.
This is for slides and there is a pointer.
Okay, great. Thank you so much.
Good evening. Welcome to CNI seminar series. Today we have Dr. Arpan Mukherjee with us. He will talk on risk-sensitive bandits, arm mixtures-optimality, and regret efficient algorithms. Dr. Arpan Mukherjee is an incoming postdoctoral researcher at Imperial College London. He obtained his PhD degree at the Department of Electrical, Computer and Systems Engineering at Rensselaer Polytechnic Institute, where he was a recipient of the B.J. Baliga Fellowship. Prior to his PhD, Arpan obtained M.Tech from the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur in 2019. He is broadly interested in problems at the intersection of signal processing, statistics, and machine learning. Welcome, Dr.
Thank you so much. Thank you, everyone, for being here. It's my pleasure, and I would like to thank the organizers for inviting me for the talk. Today, I'll be talking about risk-sensitive bandits, which is a very, very new work. And this is the first time I'm presenting it, so I would really, really appreciate your feedback on the work. This is a joint work with collaborators Meltem Tatle from RPI, Karthikeyan Shanmugam, probably you know him, from DeepMind India, Prashant Tele at IIT Madras, and my PhD advisor, Professor Ali Tajer. So let us start with the setting of multi-armed bandits, which is essentially a sequential experimental design. There is a set of arms, also called experiments, also called actions, and there is a learner. At each instant of time, the learner selects an experiment or pulls an arm, and nature generates an observation. This observation is then fed into a utility, and the learner gets to observe a noisy reward based on the evaluation of the utility of the observation. Now, in multi-armed bandits, two broad paradigms have been investigated. Regret minimization, which is the canonical paradigm in which we aim to sort of maximize the reward that we gain over a finite horizon game. For example, T is the horizon, A star is the arm which has the largest average reward, and we try to maximize the reward, or in other words, minimize the regret, cumulative regret. And the other paradigm which gained some recent attention is that of best arm identification, also called pure exploration, in which the objective is to identify the arm with the largest mean. So A star is essentially the arm with the largest mean, and we aim to identify that. Depending on the structure of the action space and the utility, there are various multi-armed bandit settings which are tailored for various applications. For example, the action space can have a causal graph encoding in it, in which case we have a causal bandit, and it finds applications in gene networks, for example. Then there are combinatorial bandits in which instead of pulling one arm, we pull a subset of arms, and the reward is a function of the observations from each of these arms. Finds applications in routing, for example, network routing. Then there are contaminated bandits in which the reward is assumed to be contaminated by an adversary, and this also finds applications in various real-world scenarios. For example, recommender systems in which user feedback oftentimes is malicious. There is restless bandits, which finds applications in healthcare, in which each arm, instead of generating IID observation, is assumed to follow an underlying Markov decision process. And of course, the most traditional canonical framework is stochastic bandits. There are a finite number of arms. Each arm is generating reward according to some distribution, which is partly or fully unknown. And then there is risk-sensitive bandits, and in today's talk, I would be focusing on risk-sensitive bandits, which is finding some recent application. Now, what does that mean? We'll find out. So let's say we are given a particular example. There is a learner, and the learner wants to decide between option A and option B, which are essentially investment portfolios. Option A has an expected return, let's say 12% annually, but it also has a risk or volatility as, sort of variance, 30%, very high. It has a high return, but high volatility. And then there is option B, which has a lower return, 8% annually, but also a lower variance, which is 10%. So it's sort of more like it's stable in some sense. So option A has a larger variance, larger risk, but a larger reward. Option B has a smaller average reward, but smaller risk. So in such settings, the canonical objective of always trying to optimize for the average utility is not ideal. Maybe in a situation as a human being, I want to go for the option which has a lower risk. So human in the loop decision making is essentially sensitive to decision risks. And example bandit applications include clinical trials. For example, there is a scientist, and the scientist wants to decide between protocol A and protocol B. Protocol A has larger expected success, but larger variation across replicates. Protocol B, smaller expected success, but smaller variation across replicates. And probably the scientist wants to do A/B testing maybe between protocols A and B sequentially, right? In these applications, optimizing the average value is not ideal. So how do we, and we generally optimize for risk. Question is, how do we sequentially control risk? So the answer is simple. In the utility box, we go for risk-sensitive utilities, which are essentially functions of arm distributions themselves instead of just, let's say, the first moment. Examples of such risk-sensitive utilities include variance, CVAR. There are others like Gini deviation, Sharpe ratio, many others. Now, the nomenclature of the literature on risk goes as follows. So in this talk, we would look at this bigger umbrella. It's called distortion risk metric. It has been termed by Wang et al. From 2022. The way it is expressed is as follows. For a particular distribution P, U of P, which is the utility evaluated at P, is essentially in the form of an integral, 0 to infinity. H, which is essentially a distortion function, which distorts the cumulative distribution function or complementary cumulative distribution function in a certain way. The properties of H generally is that H is a function. It's a mapping from 0, 1 to some 0b, some bounded utility. And it is generally assumed that H of 0 equals 0. Now, distortion risk metric again can be categorized into two specific categories. One is risk measures and the other is deviation measures. Now, risk measures essentially involve distortion functions which are monotone and translation invariant. Examples, and these are what we have most commonly seen, such as the value at risk, conditional value at risk, expected shortfall, quantile-based measures. And there has been investigations focusing on risk measures. On the other hand, there are deviation measures which do not satisfy many of the properties. One of the most important properties is that it may not be monotone. Generally, CVAR, variance at risk, etc., they have monotone distortion functions, but deviation measures may not have monotone distortion functions. They are generally concave or convex. Examples include Gini deviation, mean median deviation, interquantile range, etc. Now, linking, yes, this P, it's a distribution, yes, it's a measure. I have not introduced a bandit for now, it's just a measure. If for any specific measure, we have U of P. Yeah.
So what is deviation and the risk measure is utility?
Yes, both are utilities. Depending on the properties of the distortion function, they are categorized into risk measures and deviation measures. So risk measure measures only the risk, deviation measure sort of measures it's a measure of variation, variability. It looks at sort of, how much we can gain as well as lose. So variance is a deviation measure, whereas CVAR, which looks at the tail, is a risk measure. Linking bandits and risk-sensitive utilities, there have been some sporadic investigations. For example, on quantile-based measures, we have some investigations, Soreni et al. On regret minimization, David et al. Best arm identification, Zhang et al. Best arm identification. Focusing on CVAR, we have Baudry et al. Regret minimization, and then Agrawal et al. Best arm identification. And then there were some investigations trying to unify various risk measures into one investigation. There has been a paper from Aditya Gopalan in 2017 doing regret minimization for distortion risk measures. Distortion risk measures essentially they are also a unifying umbrella, but they assume a monotone distortion function. Then there is an investigation by Castle et al. From 2018 and later 2023 who look at a broader class of risk measures they term as empirical distribution performance measures. And then there is an investigation by Chang and Tan looking at regret minimization for EDPMs, and then certain bounds in that were improved in yet another paper, Prashant and Bhatt, regret minimization 2022. Now, there has also been two different objectives that has been investigated. A majority of the investigations have focused on minimizing risk. It looks more natural to minimize risk. But there have been few investigations which maximize risk. And this becomes important because maximizing risk also is an important objective. Why? First of all, maximizing risk translates to looking at gains instead of losses. For example, CVAR can be defined both on the right tail and on the left tail of the distribution. When CVAR is defined on the right tail of the distribution, it means we are maximizing risk because we are looking at how much maximum gain we can derive, right? So maximizing risk measures do make sense. And for example, Baudry et al., they maximize CVAR, Castle et al. Maximize CVAR. Khurshid et al., very recent investigation, they try to maximize variance in order to eliminate high volatile arms, okay? For this work, I'll focus on unconstrained maximization of risk measures. And it has applications, for example, in high volatile trading, where traders seek to go for the riskiest policies. And maximizing entropy-based deviation measures, for example, Tsallis entropy is known in the finance literature. So you basically want to get rid of arms which have a huge variance. I don't want arms which have like too much. Yes, the objective of the problem is to get rid of those arms, but we have to identify those. That's, yeah. So it's important to consider Castle et al. Yeah. Yes. Yes, or in other terms, even a more refined objective, which is constrain the variance, optimize for average, constraint. These are all different objectives that have been investigated. But even looking for high risk is also something that is considered in the finance literature, essentially for this application of high volatile trading. So essentially there we don't want to minimize risk, we want to take risk. And so even unconstrained maximization has yes. So the entropy is one measure that they look at. Many of the risk high entropy, essentially they want to take risk. Even if they lose, they don't care. They want to take risk. Yeah. So there are investigations which look at sort of maximizing risk. One of those investigations from Colt 2018 is by Castle et al. They look at empirical distribution performance measures. What is that? First of all, they define A star as the arm which maximizes risk. It's essentially U of Fi. So now we have K arms. Distribution of each arm is denoted by F sub 1 through F sub K. A star denotes the arm which maximizes risk, and they define the goal as average regret minimization in the following sense. So U of F A star is essentially the maximum utility that you can get, but you don't know A star. So you try to come up with a policy pi. Nu is the bandit instance. You take an average of u of summation I in k tau t pi I. So tau t pi I is essentially how many times you have chosen arm I divided by the horizon. So that's like the empirical fraction of times you've chosen an arm I, fi. So that's a mixture distribution. Why a mixture distribution? Because when you sample arms, the rewards follow a mixture distribution in the space of arms. They make the assumption that the utility is convex. They also make the assumption that the utility is stable in some abstract semi-normed space. So let us start with the setting of multi-armed bandits, which is essentially a sequential yes, that is correct. That's pretty much it. There are some nuances that get into it because of the utility. Essentially, you have to deal with. Yes, the formulation of the problem that they have is pretty much the same as canonical bandits. They make some assumptions, and yeah, for example, Lipschitzness, stable in some abstract semi-normed space, etc. And essentially, these drawbacks is what we try to address, we try to attack in the paper. So what we show is that this simplifying assumption that there exists like one solitary best arm, which they call A star, which essentially translates the problem into something very similar to canonical bandits, does not always hold. I have a counter example in this slide. So this utility, it's called Gini deviation. The utility is essentially u of f, let's say f, consider f to be Bernoulli. It's like p times 1 minus p kind of a utility. In this particular utility, convexity does not hold. It's a concave distortion function and utility. And also it's non-monotone, so it does not fall in the regime of risk measures. For this particular case, we show that there is no solitary best arm. So for example, here in this diagram, there are two arms. Let's say the first arm has, it's Bernoulli with mean 0.1. The second arm is Bernoulli with mean 0.7. Essentially, we see that a mixture of these two values essentially is maximizing the utility, which is 0.5. So if we take some alpha fraction times 0.1 plus 1 minus alpha times 0.7, that is where we maximize the utility. So no solitary arm is optimal. Rather, the optimal utility is essentially a mixture. And when this happens, a lot of things break down, because the whole analysis around multi-armed bandits is assumes the underlying solitary best arm. And then investigations, I mean, the way things are analyzed is suboptimal arms should not be sampled too often. So that's. No, this is what we observe and we investigate. Kessel assumes that there is a solitary best arm, but we say that that is not the case. Concave and non-monotone. And then there is risk-sensitive bandits. Yes, yes, yes. So we try to ask this question: can we construct regret-efficient algorithms for risk metrics which have optimal mixtures? Okay. So no solitary best arm, rather a mixture policy is optimal. And the key challenge here is that instead of a detection problem now, we face an estimation problem, because we need to estimate this optimal utility, optimal mixture alpha, right? So the question is how to track mixtures. Yeah. It has a high return, but high volatility. Then there is option B, which has a lower return, 8% annually, but also a lower variance, which is 10%. So it's sort of more like it's stable in some sense. So option A has a larger variance, larger risk, but a larger reward. Option B has a smaller average reward, but smaller risk. So in such settings, it is muted. You know, the canonical objective of always trying to optimize.
I just unmuted. You're being recorded to remind me.
Okay. As a human being, I want to go for the option which has a lower risk. So human in the loop decision making is essentially sensitive to decision risks. And example bandit applications include clinical trials. For example, there is a scientist, and the scientist wants to decide between protocol A and protocol B. Protocol A has larger expected success, but larger variation across replicas. Protocol B, smaller expected success, but smaller variation across.
Control L, I guess.
And probably the scientist wants to do A/B testing maybe between protocols A and B. Okay. Okay. So we formulate a revised objective, which is regret with respect to an infinite horizon. So we look at a revised objective. Now we are saying that we cannot define regret with respect to a solitary best arm. Instead, we must consider an infinite horizon oracle policy, which is essentially the mixture policy. So this oracle policy is the policy that attains the maximum utility, which we denote by alpha star nu, which is a mixture distribution over the arms, which is arg sup. Why? Yes, so why I call it infinite horizon oracle is because if we look at a finite horizon T, maybe no policy can attain this alpha star. Yes, but I call it infinite horizon because essentially it's just a nomenclature to denote that this alpha star nu, it can even be a fraction, like 0.3333 so on. And then we redefine the goal as follows. So here, instead of the red, red portion, we had u of f a star, which was the best, but we have u of alpha star nu I fi. And the task essentially, if you look at this sort of regret, we want to converge our sampling fractions, which on the right hand side is tau sub t pi I over t, to this alpha nu star. That's what we want to do in a regret efficient way, essentially. And the assumption I only make is Holder continuous utility, Holder exponent is q. I do not assume Lipschitzness or anything else, convexity, etc. Now, in terms of algorithm design, it's Holder continuity means, like, let's say you have CDFs f and g. So uf minus ug would be upper bounded by some L times norm f minus g to the q. Distributions, yes, CDFs. uf minus ug is less equals L times some norm of f minus g. So it's I'll mention it's the Wasserstein distance between f and g to the q. L is like a coefficient, so it's like the Lipschitz constant.
But you say that is on only the exponent.
Yes, if it's Lipschitz, q is 1. Yeah. So some of the when it comes to algorithm design, first it's important to discuss that some of the attributes of canonical algorithms do not work. First thing, what canonical algorithms do is that they identify the suboptimal arms by sampling them at most order of log t times. So the thing is, like, for example, if you consider UCB or for that matter any regret efficient algorithm, they are based on the fact that you cannot explore a suboptimal arms more than order of log t times. Then you have a bad algorithm. But this notion does not work in our case, essentially because we do not have something called suboptimal arm. We have mixtures. The next thing is risk neutral algorithms. They are generally parametric in nature. So risk neutral is what are basically algorithms which look at average value. They are generally parametric in nature. For example, you can look at linear bandits, or you can, it has a parameter as theta. Stochastic bandits has the mean values as a parameter, etc. In the risk sensitive setting, we are facing non-parametric scenario. We have the entire distribution. So it entails all the higher order moments, not just the first moment, etc. The third challenge, now when you go to risk sensitive bandit literature, for example, Castle et al., as I discussed, they have strong assumptions. Now what are these assumptions? First assumption is that they assume that the utilities are stable. What that means is they assume exponential convergence of CDF estimates in some abstract semi-normed space. So if you form a histogram from any arm, this particular histogram converges to the true CDF at an exponential rate in some abstract semi-normed space. They don't really specify in which cases we can have such exponential convergence, and it actually may not hold in all scenarios, let's say. And they also assume convex utilities, which leads to the main focus of this investigation, which is solitary best arm.
So when you say this suboptimal, you can always sort of discretize your parameter space, like create some alpha norm balls, and just as long as you're in epsilon norm ball of good arm, right?
Yes. So that's the thing. For example, you do not have an epsilon ball of the good arm. So do you mean like the optimal mixture is, let's say, for two arms?
Let's say there's a single optimum mixture, right? There's a single point, right? This is a vector in the end, right? Alpha.
So it's like 0.3, 0.7.
Yeah. So
that's optimal.
Then you can sort of like find the epsilon ball around it, which is like 0.35, 0.65, whatever, right?
Yes.
And all those would be okay. And then you can again say, like,
if you deal with it exactly in that way, you can run into.
But I'm just saying this is one of the options.
Yes, that is something also we explore. So we have explored that particular opportunity, and yeah, we will discuss. Our algorithm is something along those lines.
And the second part is like, when you say non-parametric, right?
Yeah.
Then how do you do it? Because again, like you sort of have to, you will still have to do some kind of quantification, right? Otherwise,
Yes. So
you have only finitely many samples. Like you have infinitely many samples.
exactly. So we construct CDF estimates from. So we construct histograms from those samples. Yeah. Yeah. Okay. So the algorithm design, essentially, as you mentioned, it will have two components here. First, we have to estimate the mixing coefficients, but we have to see that we do that in a regret efficient way, not just any estimate. And then once we have estimated those coefficients, the other task is to track the estimated mixtures. Because remember, from the regret definition, we want essentially this quantity here, which is the arm fractions, to match alpha star. So we have to keep that in mind, that once we have even estimated what's the true alpha, we have to make our sampling fractions to converge to that particular alpha. So for the first part, estimating mixing coefficients, we explore two ideas. A very basic idea, which is explore then commit based idea. That's where any Bandit book starts, but it has its own drawbacks, as I'll discuss. And then I move into a UCB based method for doing it. And for tracking the estimated mixtures, we propose something called undersampling, which is an efficient method of tracking mixtures, as I'll show. So for component one, which is essentially estimating mixtures, the first algorithm we propose is risk sensitive explore then commit for mixtures. We call it RSETCM. Follows the explore then commit kind of a strategy, that is explore in the first half, let's say, and form a reliable estimate of about what is a good alpha, and then sample according to it. That is essentially the thought process here. So the first part is estimating mixtures. For doing that, we estimate CDFs, and for doing that, we draw each arm, let's say some n epsilon over k times. I'll say what n epsilon is. So for now, just assume that we draw each arm a certain number of times, right? And we form CDF estimates out of these arms. Once we have formed the CDF estimates, we simply pick the alpha that maximizes the utility. But here comes in exactly what Professor mentioned, which is discretization. So we discretize the simplex, that's the idea. And this is important in the following sense. If we discretize the search space, one thing is, if we have plug-in estimates, that is, if given a particular value of alpha I and these guys, if there is a plug-in evaluator, we can this estimator always exists, right? So computational tractability is the first advantage that discretization gives us. And as Professor also mentioned, it transforms the problem into a finite armed bandit instance in terms of discrete mixing coefficients, let's say. So that is why we look at discretization. It's important. So once we form a good estimate of alpha and epsilon, now what n epsilon? So epsilon is the level of discretization. So along each coordinate, essentially we discretize into epsilon intervals. Of course, constrained to the simplex constraint. And n epsilon is a quantity which depends on instance dependent information. For example, it's also the case in canonical ETC algorithm. It depends on the gap information, etc. This n epsilon quantity is also something that depends on CDF information, essentially. And that is a drawback, known drawback of ETC algorithm. Now, once we have estimated the alphas, the second part kicks in, which is essentially how do we track? And it's a very simple policy. Choose the first k minus 1, and that is, you can, instead of the first k minus 1, you can pick any k minus 1. So this set S is defined as the first k minus 1. And then you go ahead and select that particular, those arms which are in this set, like, the first k minus 1 arms, a maximum of n epsilon over k or t alpha hat n. So t alpha hat n is essentially the quantity you would sample those arms in order to go the closest. But what might happen is exploring n epsilon over k times, so this quantity might be lesser than this quantity. So you don't want to oversample anymore. So you sort of cut it down to n epsilon over k, and whatever remaining budget you have, you assign to the one remaining arm, which is the kth arm. And instead of the first k minus 1, you can go for any k minus 1, it works. So so it's a very simple algorithm, but it has this major drawback that it kind of depends on instance dependent parameters, and we don't want that. That is the reason we want to go to UCB. Yeah, yeah.
So here you took some set of k minus 1 arms.
Yeah.
To begin with.
Yeah.
And then what you're doing, so you said minimum, but then there's written maximum, right?
No. So
Cut it down, you said.
yeah. So what I mean is, so you use a particular budget to form estimate of alpha of
N epsilon by k, right?
n epsilon by k for each arm. So overall it's n epsilon. After that instant, what you do is whatever alpha you got, you multiply t times alpha hat ni for each arm. What might happen is this quantity could actually be smaller than n epsilon over k. Then essentially I don't sample that arm anymore. If t alpha hat is more than, so let's say t alpha hat is 20, but I have already pulled that arm 22 times, then I'm not going to pull it anymore.
But this, how do you know this alpha hat is something you're estimating, right?
Yes, I estimated it in the previous step.
Okay. This is what you're looking for.
Yeah, yeah. So that's, yeah. Great question. So if you go back to the regret definition, what we want is not alphas, but we want our arm selection fractions to match alpha. So even if you have estimated alpha, we have to match our sampling fractions to it. Yeah, that's the reason why.
They should be close, right, in some sense.
Not always. So let's say you are doing, for ETC, right, you use the budget of n epsilon over k.
Maybe you're right. So what you're trying to do is that I found alpha.
Yes.
Now I need to find the other, whatever the fraction is in iterative way. Is that that's what you call tracking?
What I call tracking is as follows. So at instant n epsilon, my sampling fractions is 1.
No questions. Yeah, no,
Yeah.
that's it, right?
Yeah.
So here, what is it you want to do? You want to minimize this regret.
Yes.
So if this is 0, great. If it's not 0, then what is that you're trying to solve? So you found this alpha star, which is
Yes.
the soup of the previous problem.
Yes.
Now what do you do? What is your
Once I found that out, it does not mean in order to find this out, this guy also has to be alpha star, right? Because this is how many times I have pulled the arms in order to estimate the alpha, right? Because if you look at the ETC algorithm, that this tau ti over t is essentially 1 over k at some point. It's 1 over k, 1 over k, 1 over k. But it's not enough because let's say for 2 arms, it's 50%, 50% now, but I need to be close to, let's say 30%, 70%. That's the optimal alpha that we found out. So we have to, resample in a way that I move my.
I understand. What am this question, my question is different. I'm trying to understand what is the objective, like what is it that you're trying to do? Like, so for example, I was trying to find minimum, I do gradient descent, right? What is the tracking algorithm doing? What is the objective of the tracking?
Right. So tracking algorithm is trying to get my arm selection fractions close to alpha, not just estimate alpha.
That's all.
That's all. Yeah.
If you already sort of know alpha, right? Once you know what the fraction is going to do.
Yes, but remember, the definition of regret is this. Okay, if I know alpha, this regret can still be very large. If this regret was defined in terms of the alpha that I estimated, then great, I'm done. But this regret, the way it's defined here, it could still be very large. And the reason we define it in this way, it comes from the previous existing literature.
But I'm still because you said in the end you want your fraction to be close to alpha, right?
Yes.
So then what is that? I found alpha, then I can find fraction. I just multiply by t and I said this is my fraction. That's it.
No, but it's not something. So let's say, as I mentioned, like let's say at time instance 25, I have pulled, or time instance 26, I have pulled arms 1 and 2 13 times each.
Okay, you're saying that you have to maintain this fraction going forward as well.
Yes. Yes. Okay. So of course, ETC has this problem of knowing instance-dependent parameters. In order to mitigate this problem, we go to a UCB-based approach. Again, we have the two components. The first component is estimating mixtures. And in order to estimate mixtures, now we want to do it in an optimistic way instead of ETC, which, sort of. So what do? First thing that we do is some forced exploration. Now, forced exploration might sound weird because it's absent in canonical bandits. We do not do it. But we do this to form reliable estimates of the CDF. And I don't know if this is visible, but for each arm, we sample at the very beginning, we sample each arm some zeta t times, where zeta is some small hyperparameter. No? I think we can, yes. Yeah. So we draw each arm zeta t times, so zeta is a hyperparameter. And the reason we do it, okay, so forced exploration is absent in canonical UCB. The reason is that we should not actually oversample. So we should not sample suboptimal arms more than log t times, let's say. But in the case of mixtures, it might happen, for example, this 0.3, 0.7 case, where there is nothing called suboptimal arm, and both the arms need to be explored in a linear order, right? So that's the reason we do a very tiny level of forced exploration. Coming up with a regret efficient algorithm that implicitly does this linear order of exploration, as in UCB, is definitely something we have been thinking, but we don't have a concrete answer yet, and is definitely an open question.
One thing which I think is like also not happening is that what if your alpha sort of is 0 for certain arms? You would want to sort of discard it, right?
Yes, that is actually a great question.
In your mind is that alpha is going to be sort of non-zero.
Yes.
For every arm, so that's why I need to explore, right?
Yes, yes. That is actually a very good question. So if we do, so there are different viewpoints. These are all, the directions in which we are thinking. What might happen, and there are examples in which, let's say, just two arms they have non-zero weights, and all the other arms have 0 weights. But there is no way of knowing them a priori.
I agree, but this is now sort of like compressed sensing style.
Yes.
You know that.
Yes, we can. Let's say it's like a D sparse vector or something like that.
So you know that your alpha is only support, which is much smaller.
Yeah, if we have that information, we could actually improve our algorithm to
Start with that assumption and see if this helps.
it would absolutely help. That's my guess. I don't have a proof for it, but I'm pretty sure that it would help. Translate, so I do not exactly give the regret bounds because they are big expressions, but on a high level, the regret bounds are of the order of k being the number of arms. My guess is that k would be reduced to, let's say, 2 or 3, which is the sparsity, whatever the support is, yes. Yeah. Yes. Yes. Yes, zeta t times, but this zeta is not instance dependent. Zeta is some small thing you choose. It could be 0.001. N epsilon was depending on instance dependent parameters, which are essentially functions of the CDF. But this zeta could be anything. You choose. Yeah, it is a hyperparameter. It only matters in empirical results. It does not really matter in the regret upper bound, let's say. So regret, but since zeta is bounded away from 0, I don't care about it. All I need is it has to be bounded away from 0. You can make it as small as possible. Yes, absolutely. Yeah. So okay, so we sort of went over the open question here. But okay, now the more important step is essentially estimating the optimal mixtures. So we form CDF estimates, of course, that's the first step. Once we do the CDF estimates, now the estimate alpha is sort of an optimistic estimate. So we plug in a UCB style utility for it. So FTIU is essentially my estimated CDF. And for a specific alpha, this is just the alpha. So fix an alpha, then this first quantity is essentially the estimated utility, and then we have some upper confidence bound here. L is the Lipschitz constant, as I discussed, and for this particular confidence bound, we assume a bounded support for the distributions, but we can, I'll discuss it, we can easily get rid of it using some technique. But for this expression, we assume bounded support, and diameter is essentially the support, the diameter of the support. And we have this UCB style utility, and the mixture estimate essentially becomes this. So instead of maximizing just the estimated utility, we maximize the estimate plus upper confidence bound.
So is it the true upper confidence, upper confidence bound, what do? You look at the average plus the variance in the estimate, right? And
right.
take the most likely high reward arm. Here, what is the interpretation of the second term?
Yeah, this is essentially the variance kind of term.
Again, so
yeah.
That if this is the mean, sort of the
it's not okay. So I should not. Yeah, that I should correct myself. It's not variance, but because this is the objective essentially involves all the higher order moments, but this term essentially controls the following statement. So this term is based on a high probability event. The event is that the true CDFs are contained inside a ball around the estimates. That's all. So I'm not sure whether we should call it variance.
That is your diameter I. Is that the ball?
The ball is essentially this whole thing, right? So FTIU is my estimate of the CDF, and this is the ball. Alpha I, for a specific alpha, it's alpha I. Diameter is essentially the support length. So if it's 0, 1, it's like 1, and log T over tau, which is also seen in upper confidence bound algorithms, right? And I think so. This diameter can be interpreted as variance because bounded support distribution means it's like sigma, like the support sub Gaussian, right? B squared over 8. So you can think of this term as variance, but
Because if you look at the distributions, they are not like normal objects like mean, right?
yes.
So this part I'm having trouble understanding.
So this ball is a one Wasserstein ball around the estimate of the CDF, and what this ensures is that the CDF, the true CDF, is contained inside the CDF, the one Wasserstein ball around the CDF estimate with a probability at least 1 over T squared. That's the interpretation of it. So once we form that UCB for every alpha, we pick the alpha which maximizes the UCB, and that becomes my estimate for alpha, the mixing coefficient. Once we have estimated, again we have to track, but here we do tracking a little differently. This is something that I have, you can say, borrowed a little bit from my best term identification work, but we do something called undersampling, which is as follows. So alpha T is essentially the estimate that we formed in the previous slide. T times alpha T is how many times a particular arm should be sampled. We look at this difference, that how many times it should be sampled versus how many times it has been sampled, and we choose the arm which minimizes this quantity, so which is the most undersampled, and we keep doing this. One idea could have been just randomly sampling according to alpha T. It's a naive idea, but empirically this one performs much better than randomly sampling from alpha T. That's the reason we analyze undersampling as a way of tracking mixtures.
I didn't get it. Like sample the one which is most undersampled, or
most undersampled, yes.
but that's not really undersampled. Like you're trying to sort of balance it out.
Yes.
Being undersampled,
So undersampled means it was a
but the nomenclature is bit.
yeah, the nomenclature is also something that exists in the BAI literature.
It's terrible nomenclature.
Yeah.
You are just trying to do some sort of equalization. If
Yes.
you sample enough, I'll give you the.
Yes. I agree. So the takeaway is that there is no instance dependence in this whole algorithm. So the first step is sample each arm zeta t times. Zeta is some small number. Form this UCB estimate at every round after that, and essentially undersample, and that's how you continue. Okay. So now that we have discussed about the algorithm, we focus on regret analysis. We have a regret decomposition which is as follows. Since we are doing discretization, we have a discretization error. we will have a CDF estimation error because we are forming CDF estimates from the rewards. And we will also have a sampling estimation error, which is the estimation error involved in moving our arm selection fractions to the estimates. So those are the 3 error components. For analyzing the error, as I mentioned, we consider the space of distributions endowed with the one Wasserstein metric. And this is helpful. This is helpful because if we have this assumption, DKW immediately tells me that there is exponential convergence of the CDF estimates to the true CDFs, the DKW inequality. And this is also easily extensible to unbounded sub-Gaussian distributions through a paper by Prashant and Bhatt from 2022. So now we come to the key finding, and let me also, can we move this bar from here? Oh no, it's not. Okay. Oh, okay. Great. So what we observe is that sublinear regret would mean, and I think this is established by now, sublinear regret would mean we must have convergence in sampling fractions. Now, the key question is, how do we ensure that? And this analysis, whatever I mention, is for the UCB style algorithm. The ETC style is in the paper. The key finding is that UCB plus undersampling is a regret efficient way of tracking mixtures. But how? The first result that we have is, after some finite time instant t of epsilon, which depends on the discretization level, and every time instant after that point, the probability that the RS-UCBM algorithm selects a suboptimal discrete mixing coefficient is upper bounded by a small quantity. So essentially, the event that in any time instant, at any time instant between t epsilon and t being the horizon, the probability that whatever UCB selects, that is alpha t here, not being equal to the discrete optimal mixture alpha bar star, that has a very low probability. So that's the basic, the most fundamental result. Because once we form good enough estimates after a certain point, we can hope to track that particular estimate. So the key takeaway is that UCB always picks the correct discrete optimal coefficient. Yes. Yes, the overall thing is decreasing. You can multiply and see. It's like 1 over t squared to the k, and t times that. Its overall thing is discrete, and you have the -1 too. So it's a polynomial decrease, I think, but it's a decrease. And the next lemma which we have, which essentially ensures the tracking part. So undersampling ensures with high probability that tau sub ti over t minus alpha bar star I, this difference, which is the sampling estimation error, is upper bounded by k over t for all t larger than t epsilon. So a combination of these two fundamental results basically mean that we have sublinear regret. And this quantity t epsilon that I've been mentioning, it's a quantity which is inversely proportional to epsilon to the 2 over q. So it's like a finite instant. After that instant, we can assure, like asymptotically, we can assure we have sublinear regret. And something about this quantity t epsilon, larger the discretization level, the smaller is this quantity. So we ensure a faster convergence to the discrete optimal solution, but we have larger discretization error, because let's say we have just 2 discretization levels, right, 0 or 1. It would mean that we have a very fast convergence to the discrete optimal solution, but we would have a very large discretization error. So we would kind of need a balance there. So these are some of the bounds. For CDF estimation error, we have a bound which does not depend on the discretization level for natural reasons. It's like of the order t to the minus q over 2 log t to the q over 2. And we have a sampling error. I think this is a combination of the 2 results here that I mentioned, like this part and this part, right? So it's like a summation of those 2 quantities, but it does depend on the discretization level, and it holds for t larger than that quantity. And as a final step, as I mentioned, we can optimize for the discretization level in order to achieve that balance. And after that optimization, I have a list of the regret bounds for various utilities under this framework. The first 5 utilities, for example, the mean value, that's the first one. The dual power, quadratic, CVAR, PHT, these are all utilities which have a monotone distortion function. And as a result, they have solitary best arm. And we sort of provide the bounds for these guys. For UCB, we have like a square root of log t over t regret, whereas for ETC, we have a better regret, actually. And that is expected because ETC has more information compared to UCB. And we must remember that in UCB we do not know even, like, it does not utilize the information that there is a solitary best arm. So that's the reason we suffer in terms of regret. But for mixtures, for example, Wang's right tail deviation, we have, UCB wins over ETC. It has a better regret guarantee. And for Gini deviation, also okay, so sorry, for Wang's right tail, actually ETC has a better guarantee, T to the minus 1/3, whereas for Gini deviation, UCB wins. And this is a very peculiar observation that we make, because we know for canonical bandits, both ETC and UCB, they have the same order of regret bounds. Only thing is that ETC requires instance dependence, but UCB does not. But the regret bound is always of the order log T over T. But we see that in the case of mixtures, it could vary. And these and this variation is because of the properties of the utility. For example, the dependence on Q, and also the dependence on some minimum gap information, etc. There is variation because of the utility. So if the learner knows which utility they're optimizing for, they could choose either ETC or UCB, provided they have appropriate gap information. And these are some empirical evaluations where we pick Gini deviation as the utility, and it's a simple two-armed case, and we show that actually UCB, as we put in the table, UCB performs better. It's the black line here. It performs better than, let's say, the RSETCM. And the regret is constant because after n epsilon, it kind of picks, like we pick a particular alpha. There is, at time instant n epsilon, we pick a particular alpha and we track that. But in case of UCB, the alpha t estimate slowly converges after that point. So, okay. The next important question that we try to answer is whether or not we can have a lower bound to support the results that we have in terms of the upper bound. Now, this is also a little tricky because of the following reason. The idea for canonical bandits in terms of lower bound, minimax lower bound, is as follows. First of all, you decompose the regret in terms of suboptimality gap and the number of times you choose suboptimal arms. Then what you do is you construct a principal and alternate bandit instance, right? And then you say that, okay, the principal, how do you construct them? Principal and bandit instance is almost the same except one suboptimal arm in which you put a little extra quantity, and you use change of measures to argue that no policy can have small regret for both cases. However, issue here is it's simple. There is nothing called suboptimal arms. So how do you essentially come up with a minimax lower bound? The way we deal with this problem is as follows. The key question is, the first key question is, how do you decompose regret? We still pick Gini deviation as the utility because the lower bound would actually depend on the utility. We cannot have a lower bound which is, rather I should say, we cannot have an algorithm that is agnostic to utility. That is impossible. We have an impossibility result which says, if you have a lower bound, if you have an algorithm which is agnostic to the utility, you'll always incur linear regret for some particular, like minimax linear regret. So we pick a particular utility, which is Gini deviation, and then we revisit the discretization idea. We choose a discretization level epsilon, but the way we do discretization is a little different, and this is as follows. Let's say it's a two-armed case. On this line, horizontal line, we have the alphas, and these are the discretization levels, 0 and 1, right? We do the discretization, let's say this is the true alpha, alpha star is what I denote. We do the discretization in a way that this alpha star lies in the center of one of the bins. And this is always possible because we can make the first and last bins arbitrary size, like small. And this is important, we'll find it in the analysis. And we denote this particular bin in which alpha star is contained by b nu star. And with this particular discretization scheme, we have a particular regret decomposition, which is as follows. The regret is lower bounded by some delta min nu epsilon quantity, which is essentially this gap. So what is this gap? Delta min nu epsilon is the difference between the maximum utility and the utility evaluated at any other alpha from a different bin. So for this case, it is essentially this bin, and we pick the alpha. This is the closest one, and it's essentially the gap. Okay, so it's lower bounded by this minimum gap times a probability of error quantity. It's nu is the bandit instance, pi is the policy. Alpha hat sub t pi is essentially what is the sampling fraction provided by the policy pi at the end of the horizon, and the probability that sampling fraction is not contained in the correct bin. So that's like a probability of error term. That's the regret decomposition we can have. Once we have that regret decomposition, we kind of get back to the idea of constructing principal and alternate bandit instances, but there are major distinctions. So what we do is we construct a principal instance. Let's say two-armed case is like Bernoulli P, Bernoulli 1 minus P. And then we construct two alternate instances. One is like instance new 1, which has a little bit delta amount added to the first arm, and an instance 2, which has a little bit delta amount subtracted from the second arm. That's how we do. And for any k between, because it's two-armed case, the minimax regret is actually lower bounded. So this is essentially lower bounding minimax regret first by the Bayesian regret. And then we essentially use this regret decomposition here, and we do a little trick in terms of the probability of error. So for the first one, it's the probability of error, and for second one, it is also the probability of error. So essentially, we recover a structure which is known in the bandit literature, because now we have some measure P of event A plus measure Q of event A complement. That's what we are going for, because once we have such a decomposition, we can now go back to, let's say, ideas like lower bounding by TV distance, Brutagnol-Huber inequality, and we can get what we want. But before we go there, the thing that we, as I mentioned, like it looks familiar, lower bound using total variation to Brutagnol-Huber, but we have to ensure that these are actually events A and A complement. So we have to construct these instances in a way that this is an event A and this is an event A complement. Now, in order to have that construction, we need two properties to be satisfied by these instances. The first property is that the principal and alternate instances should have different optimal bins. They cannot have the same optimal bin if you take any two. And we have to satisfy the property that the alternate instance cannot be too different from the principal instance, right? So in terms of KL divergence, like 1 over KL divergence between the first arm of the principal instance and the first arm of the first alternate instance, plus inverse KL divergence of the second arm of the principal instance and the second arm of the second alternate instance, they are lower bounded by T. What that means is the KL divergence is actually small, like if you invert it, it's sufficiently small. So if we can construct instances in a way that these two properties are satisfied, then we can use this Brutagnol-Huber idea to come up with a lower bound. And turns out that, okay, so the question is how to set P and delta. These are the design parameters of the instances in a way such that P1 and P2 are satisfied. The answer is that we can set P is equal to 0.5 plus some quantity eta. You can choose eta to be anything like 0.01. And we have to choose the discretization level epsilon, because this regret decomposition is essentially valid for any discretization epsilon. So we can choose a particular epsilon to come up with a lower bound. And the way we choose it is epsilon is set to delta over 4. Delta is a construct of the bandit instance, and we pick delta to be 1 over square root of t. So these are certain design choices we impose in order for properties P1 and P2 to be satisfied. And once we have that, the final step is to lower bound the minimum utility gap. And for the Gini deviation case, we find that the minimum utility gap can be lower bounded by 1/4 epsilon squared eta squared, where epsilon is the discretization level, eta is coming from here. And with all this combined together, we have the lower bound that for Gini deviation, bandit instance 2 arms, the minimax lower bound is of the order 1 over t. Okay, and I remarked that the upper bound we obtained was square root of log t over t for Gini deviation. So there is a gap between the lower bound and the upper bound. Okay, so we discussed some takeaways. First takeaway is that risk sensitivity, it's an important aspect for human in the loop decision making, and existing algorithms work only for solitary arms. And the key observation we make is that solitary arms is always not the optimizing solution, and there could be optimal mixtures. And we provide two algorithms, RSU-CBM and RSE-TCM, which are sort of regret efficient, and they can track mixtures. And the key idea for the, let's say, the UCB algorithm is to form optimistic estimate for mixtures and then undersampling for tracking mixtures. Now, there are several open questions which still need to be answered. Of course, the first question is closing the regret gap. So we have order of square root of log t over t for the upper bound, and lower bound is omega 1 over t. Can we close this gap, or is it even possible? We don't know. We had tried ETC and UCB based strategies, and there is still a gap. So the question is, can we develop algorithms for that? And also, can we incorporate the dependence of the number of arms k? Currently, this dependence on the number of arms k gets lost in the lower bound. And that is why we focus on the two-armed case. So can we bring that notion in? This becomes especially important because for the Gini deviation case, as Professor mentioned, it turns out that only two arms have, they are non-zero, and all the rest of the arms are zero. So there is the question of a compressed sensing kind of idea that there is a finite support which may not be k. And the next question is, can we devise instance-dependent lower bounds? So we investigated minimax lower bounds. Still, there are several open questions. So instance dependence is another thing that is worth investigating. And I should mention that even for the case of solitary arms, for a unified framework, there are no existing lower bounds. So there are lower bounds for CVAR, but there are no existing lower bounds for unifying framework. For example, EDPM, Castle et al. Essentially leaves lower bounds as a future direction. The third question I would like to pose is structured bandits, essentially extending the results to settings such as linear bandits, causal bandits, restless bandits, etc. And the final question, can we derive exponential convergence for CDF estimates for heavy-tailed distributions? So for sub-Gaussian case, bounded support, etc., we can take help of DKW, truncate the support, have some exponential convergence, and essentially make the algorithms work. But whenever we go to heavy-tailed, instead of exponential, the existing results only have polynomial convergence, which extremely hurts the regret. So can we derive exponential convergence in CDF estimates for heavy-tailed distributions? And of course, what would be the performance guarantees based on those confidence sequences? So that was me for today, and I'm open for discussions.
Any questions?
And we have a sampling error. I think this is a combination of the two results here. Yeah.
Some refreshments are being
This
served.
part and this part, right?
So we can take discussion and do that. Thank you.
Okay. And after that